maybe for you, maybe for some of you, it's the second competition, but for me it's the first, so it's still. My name is Haw Whammy from National Taiwan Normal University, and it's a pleasure to be the chair of the jury for this competition. And today we will have two teams for the competition. One is from 陆军官校雾里看花 the other is from 成功大学Explosion, team Explosion. So, and now they have automatically decided which is team A and which is team B. And I think team A is 陆军官校. So please introduce your team member to the audience.
I'm from our senior academy, and I'm the reporter, Zhou Chengwei. And here are our teammates. And first is Zhang Yuchang. And the second, Wang学正. Third, Zhong Wanyu. And the fourth is Li柄漪.
Thank you. So, team Exlosion, please introduce your.
I'm the presenter, Chen Xing, and we are from National Taiwan University, and these are our teammates.
I'm 蓝光培。李柄漪。谢夏。
It's a pleasure, thank you.
Now, let me introduce the other jurors, the other more important jurors. So, the first one is Professor Lin Zhongyi from National Zhongxin University. The other is Professor Ye Wangqi from National Dongfang University. So I think, so just give us 30 seconds and then we'll start the presentation. By the way, so I forgot to introduce the topics. Team A, 陆军官校 will report the topic Haw Whammy, and Team B, Team Explosion will report fast track. So if you're ready, then we can start.
We are from ROC Military Academy, and here's our team name, Flower Info. And today our topic is Haw Whammy. To our team topic, here's our problem. This Haw Whammy is a mechanical choice system with a simple wooden stick, and another stick is made up of a series of notches with a propeller at its end. And when we go over the notches, the propeller starts to rotate. And we will explain the phenomenon and investigate the relevant parameter. According to our problem, here's our problem analysis. The condition is we will consisting of a simple wooden stick, and another stick is made up of a series of notches. And we will change the propeller's length, and it will change the length. And we will proceeding the energy to transfer to the propeller. And our research direction to our theory is a mechanism to proceeding of energy transfer. To our experimental design, we will change the structure. We change the length of the propeller and the interval of the notch stick, and it's called the orthogonal oscillating. And we will control the rotating direction, called oscillating type by our finger position. And outline, including principle description, theory, experimental design and device, result and discussion, and the final is conclusions. Our principle description. In this picture, you can see the simple wooden stick pull over the notch stick and let the collect energy to act on notch stick, and the energy through the nails straight to let the propeller cause an has an orthogonal oscillation. And our theory, the flat energy K equal to F ns times velocity squared. And the K is kinetic energy. Ns is the mass of the simple stick. V is the flow velocity. And this is the energy of the propeller by the rotational motion. And this is also means orthogonal oscillation. The total energy E equal to kinetic energy plus potential energy. Because of the potential energy equal to 0, so the total energy equal to kinetic energy. And the kinetic energy transfers to the rotational kinetic energy and equal to F I times omega squared. And I is the rotational inertia. And omega is the angular velocity of the propeller. To our experiment, because we use the shape of the rectangle type of the propeller, and we use this formula to extend this I. And our propeller's width is in 1.7 centimeters. And the length of the propeller, we use 6, 9, and 12 centimeters. And our device, part 1. We use soft pressure to catch the angular velocity of the propeller. And we use voice frequency detector and camera to detecting falling energy. And this is the fixer. We fix the plastic on this equipment. And our device part 2. This is the simple wooden stick. We use it to grab the plastic. And this is the working scale. We detect the mass of the propeller. And this is the nail. And the final is the propeller. It's 3 types of the shape, the length. In our design part 1, we change port direction. And in our experimental conclusion, the propeller rotate type will not change by pull or push the over notches. And our design 2, we change the third kind of the length of the propeller in 6, 9, and 12 centimeters. And this is the result part 2. This is in these 3 figures. The voice frequency strength first time figure showed oscillating energy almost the same. You can see in the third picture, the voice frequency we test is almost the same. And this is to test that we use the same strength to travel the notch stick. And this form, we can see the length of the propeller increased, and the rotational inertia will increase too, but omega square will increase. But with the rotational kinetic energy will in an error of 2%. And this is our plot of the 3 kinds of the propeller. We can see we use the longer propeller. We use the low velocity, the angular velocity at gate, and the design 3. To change the interval of notches, we fix the length of the propeller in 10 meters, and fix the number of notches 8, and interval and use 3 kinds of notches: 0.5, 1, and 1.5 centimeters. And you can see in this picture. And in this picture, we can see the voice frequency show we use the same strength to clap and to clap the notch stick. And in this picture, you can see in the beginning, the shortest interval we use, it has a more high angular velocity in the beginning. But final, it will have a stable velocity because we use the same popular length, the same length of the propeller, and we use the same strength to carry energy to carry the and our design 4, which we took research the rotating type control. We control clockwise and counterclockwise. we control the rotating type by our finger position. When our thumb touch the right side of the nudge stick, it cancels the right side force to transfer the energy to the propeller. So it goes clockwise. And in the other hand, our forefinger touch the left side in the nudge stick, and it goes counterclockwise. And we can see the picture. We can see the video. Okay. Okay. Our conclusion: when the length of the propeller increase, our angular velocity will decrease. And another side, we change the interval of the notches, can change the angular velocity. Because the same propeller has the same for energy. And last, the rotation type can be controlled by the touch position of the finger. The finger position will leading oscillating energy. Thank you for listening.
Then the thing is report. So now thing is ready. Okay. Now it's Kimchi. When we go to about 10 minutes, please go.
Okay, we are Team Explosion from National Sengkong University, and today we will bring you the problem fast change. And in this problem, as you can see in the video on the right, it starts with the same initial height, and then as you can see later, it changes. There's a difference height later. So we'll start with the problem. So fast change is a system like this, and then because it collides with the surface, it will have a slight increase in velocity compared to free falling. Okay, and our theory is the collision with the surface causes a circular motion when it collides like that, and that circular motion will increase the velocity of the system. So we'll go straight to the theory because we have much to say. When we start with initial velocity v, and then when they collide, we have a resulting velocity EV. E is a constant ratio, 1 to 0. It's a coefficient of restitution. And this will result in a circular motion as such, 2EV cos theta. And this circular motion under time delta t can be simplified in this formula. Next, in delta t, when this block falls flat onto the surface, this block up there will fall down the distance delta v times delta t, and there will be a resulting difference delta y, which will be represented in this formula. And then delta y actually causes a delta L, which is a change in length. And this change in length actually doesn't exist because this is just what we theorize. And so, in this case, there will be an increase in acceleration that will pull the second block, this block up here, down, and it will cause a delta V, an increase in velocity. And it is simplified in formula. And we take the acceleration as a constant in the time delta t. And this delta t is smaller, much smaller than the delta t before. Because the deduction of formula is complicated, so I will simplify it. Delta V divided by V is equal to this, and it is a constant regarding to theta, an angle to the surface. We make a few assumptions in this deduction. One of them is the increase in velocity due to gravity during delta t is negligible, meaning during this time, the velocity v here will increase very little. And second, the string is inelastic, which will cause a constant acceleration here because this delta L doesn't exist, it's inelastic. And so the second assumption is that the L is constant for every theta. And acceleration due to collision can be taken as a constant acceleration. This is for simple calculation. The method we use to analyze the system is that we make a three block system like this. And we only observe the velocity change in the second block. And we change three factors. One, initial angle of the block. Two, the velocity of the block, initial velocity by changing the height of the system. And third, the length of string. The experiment, we take videos 100 frames per second videos and analyze it with tracker, and we calculate the data V over V, and then we use it to get our experiment result. The material used, we use long blocks, we saw it in half, drill holes, we put markers on it, and then we strings into it, hold the heat string with the place like this, and then hold it with rod backs so that we can release it. And then we go to the experiment result. This is our experiment result. It's quite complicated. So delta V over V corresponding to angle. Different angle have different delta V over V. This is what we get. And there's a lot of oscillation of the data. It's not really perfectly occurs because there is a lot of factors regarding this collision, and there's a lot of factors involved. It's much complicated, but then from what we calculated and what we think. Comparing this our result with the delta V, delta Y formula we have for an angle, it's quite fitting and it can be taken as estimate. So now we check for the assumptions, the initial velocity by changing the height from which you release it. So before it collides, from different height you have different initial velocity. And from different height and different initial velocity, we find that even though they are from different initial velocity, they fit the curve of the data, except for this 4. The rest is okay. So for velocity 1.8 to 4/1 and above, they still fit the data. Why this still doesn't fit the data? Because of the first assumption, the increase in velocity during collision is negligible. If you start in 0 velocity, 0 meter per second, the gravity will cause a huge increase in velocity compared to 0. So this assumption cannot be used, and then so the curve is not correct. Yeah. And the collision time during collision delta t is literally very small, 0.05 seconds. And the second one is the case for this one, this great one. After collision, for some reason, we think because the string here is loose, the second block doesn't really change the angle, and from this we can deduce that it doesn't change velocity. So this system is not done correctly, this experiment. And the second thing we want to say is the independence of the third block. When the first block collides, the velocity of the second block will change, but the third block will not be affected. And this will be this third block. After colliding at 0 meter per second, the third block doesn't change angle, so we can deduce that it doesn't change velocity. And same for the initial velocity, 3.79 meters per second. It doesn't change angle. Now we change the length of the string. This system, the normal one, uses the length of 18 centimeters. Now we change this to 24 centimeters. And if this data fits under the curve a bit lower. And this is for 6 centimeters, much shorter. For much shorter, the data fits a bit higher. And it fits the data quite well. There's a slight increase. This is because when the system in tension and you release it, the tension will be cancelled and then slowly the string will be loosened, so there will be a slight decrease in length. And this slight decrease in length is affected by the Young modulus and is affected by the length of string also. So the longer the length of string, the more it's affected and the more correction you have to do to the system. And according to the data, this only affects delta V over V slightly, so you can take it out of consideration. Secondly, we say delta L is not important, but then we can actually calculate it. Delta L is actually delta Y squared plus delta X squared, and we take the square of it. And delta Y squared is this, actually take more, and delta X is this. And put everything together, delta Y actual divided by this, and this is delta Y minus the correction, and this is this before, the simplify or factorize. And the formula, we do two graphs, and the graph is with E 0.65 and E 0.7, and it fits the graph quite nicely. So what is actually delta V over V? Delta V over V is constant for all reasonable velocity. So given the initial state of the system, we can calculate the delta V. And this is quite nice because we can calculate delta V before the collision actually happened. But then we need to calculate the angle of the second block before we use it again, because the angle of the block will change after collision. So for example, if the initial velocity is 2 meters per second at 30 degrees, so from the graph, 30 degrees will cause a delta V over V about 1 right here. So we can calculate that if delta V over V is 0.1, so delta V is 0.1 times V will be 2.1. Sorry, 2.2. 10% increase. Lastly, you look at the free fall. When you have more number of blocks in a chain system, when you free fall and fast change, meaning collide with the surface, the lower the number of blocks you have, the more time difference there will be. And if you take the ratio like this, which is equivalent to delta V over V, you see that the more number of blocks there is, the less delta V over V there will be. This is because when you collide, the angle of the second block will increase. And we find that when the angle is more than 44.4 degrees, it will cause a slow change phenomenon where it won't increase the velocity, but it will decrease it by pulling the string upward. So the velocity of the second block will decrease. So the longer the chain, the more chances the slow change phenomenon will happen. And so we make a conclusion. Fast change occurs because of pulling a block due to collision. Collision causes a relative increase in velocity, which is delta V over V. The value of delta V over V is constant for all initial reasonable velocity that fulfills. Initial velocity is much higher than velocity change during collision time during gravity. And the fewer number of blocks and the total string, the more effective is the fast change. Thank you for the kind attention.
Now each team have 2 minutes for preparation. So those things please take on the stage. And now it's time for Team B to ask Team A about some questions about the topic Haw Whammy. So you have 2 minutes.
Show me the graph. Show me the graph. Show me the graph. Strength versus something. Yeah, the graph of oscillation. Show me the graph. So it's the oscillation. How do you capture the motion of oscillation?
We use the force measurement to get the velocity. To this picture.
You capture the voice sound.
Yeah, actually sound.
The sound frequency from produced from what?
Used from our videos.
No, from the pushing or the turning?
For our machine sound.
The sound pulling. Okay. Go forward. How do you calculate the angular velocity?
We use our teacher and we put the video to track the angular velocity.
How? Like how does it turn? How do you say that it turns one round?
And we use because the tracker has a slow motion, so we can measure its turns.
So do you complete one by one, or do you actually use tracker to track it?
We check.
How do you track it?
Use our phones. Tracking.
Okay. Thank you.
Time is up. Now it's time for Team A to ask Team B about the questions. Questions about fast track, please.
Design your material of
Okay, due to time constraint, I did not say, but this is how we design it. The length, we put 3 block system. So 3 blocks, and the length is constant 36 centimeters. And for each angle, in calculate 13, the length of block is 13. So this length here is 13 centimeters, and the rest will be divided equally here. But then the length here is 36 constantly for all angles.
how to make sure your angle is the same.
Use tracker. Just like you. So you put it in tracker, and then we can analyze the angle right here using the axis.
The room is not the same.
You mean this? The angle is the same, but then I have to actually do it very slowly, not slowly, very carefully to get the correct angle. Like such.
This looks like the same angle.
I'm sorry. I have to show you like this one. The angle is almost the same. Yeah. This because I have to prepare this immediately, and I don't have time for. Yeah, I'm sorry, because there's too much thing to say. We actually cannot do that. There will be a slight skew, but then we take all the data and we try to put as much data as we can and try to find a curve. So that is an error in the experiment. And we try to take out as many as the wrong one out. But then, so we have this kind of data because there will be a lot of errors.
Okay. Thank you, sir. Thank you. So both teams again have 2 minutes for preparation for the discussion. Preparation time is up, and then will be the discussion time. So for each topic, we will have 4 minutes of discussion. So I think the first 4 minutes will be both teams for both teams to discuss the points concerning the Haw Whammy, and then the second 4 minutes will. Okay. I'm sorry. So I'm wrong. So on this. On the screen, it says the first 4 minutes will for the discussion concerning best check, and then second 4 minutes will be for the discussion concerning Haw Whammy. So please start.
How to design the shape or the rope of your system? Have you changed now to do this?
I cannot change the shape of the rope. I changed the length of the rope. But I did not change the different counts. I did not do that. I did not change anything like that. And I did not change the same length of stick every time. Because there's too much data. If you look at this graph, each of these is tracker data. And each of these takes about 15 to 30 minutes to do. So it takes a lot.
Can you change the shape or you use the...
and the shape of the rod supposed to be circular. It's more efficient that way, more collision.
Did the incline of the stick affect the falling velocity?
Yes, as you can see here, for different degree, the delta V over V difference. So the delta V over V indicates the increase in velocity. So the higher this curve is, the higher the point is at the degree, the more velocity increases.
Okay. If you would use the arrow, how will the different indicate? You use the red.
What do you mean? Can you draw it out?
We use
Yes. We actually captured video of this with zero angle, and we did not actually analyze it because we think that it's the same as free falling. Because there is no circular motion when it hits the ground, so there should not be any increase in velocity. So we captured the video, but we actually did not analyze it. But then, from here, because we analyzed videos of 10 degree and for some reason we collect at 0 degree, you can see that actually it has almost zero increase in velocity. Okay, so indirectly we get the data here. Okay. Oh, sorry. Okay. So as we mentioned before, the number of sticks will affect the time falling down. So this is the one with before.
So the more you use the wooden.
The more is there, the more blocks in the chain, the less fast chain it will be. And this is because of slow chain phenomena. And the angle is too high, it causes the chain to be slower. And this actually we not set the angle to be 44.4. But then when it collides, for example this collision, of course this angle theta will be angle theta prime, and this angle theta prime will be larger than theta. So in the long run, when it keeps colliding, the angle of the subsequent block will be higher and higher till you reach about this point, and it will cause a slow chain phenomena which will slow down the chain. So the longer the chain you have, the less effective it will be.
I see you one meter. You use the hand to do the gesture.
Yeah, that's me.
It's also the artificial error.
Yes, we try to make
Please give a short answer.
Okay, we don't have time to actually make a device that actually help us release it on command. So what we did is actually push it against the wall like this. So when we release it, we just do like a slight motion. So this will cause as little as possible error. That's what we think.
Okay, thank you. Now it's time for the discussion about Haw Whammy.
Okay, first of all, are you sure that your strength used is constant every time? You say that the graph for your data, the strength is constant every time. How can you be so sure? Or is there like an error of plus and minus?
It is important to see our error increasing. This is our
How do you calculate this error? No, I mean, is it consistent? The same every time? You're not sure. Same for going speed. The speed where you do this. You're not sure. Okay. But then it's quite close. Yeah. Okay. Can you show me the graph for oscillation? Why does it oscillate like this and not constant?
Because we use the same propellers next, so it's at the same time, and we use the same strength to grab the stick. So the indicator is level velocity, angular velocity, and
Okay. So for time, this is in second. So in 10 second time, the angular acceleration, angular velocity will be constant.
yeah.
Okay. And the interval of notches doesn't affect it much. Why is this so? I mean, if you do this, and then if you have different interval, it should have different oscillation time, and then this will affect it slightly. But then why does it have the same angular velocity?
We use the same energy travel
Can you explain why it will be the same regarding of the intervals?
We pick the number of the notches, so it's the same.
Oh,
Same.
so the number of notches is the same, but the interval different.
Yeah.
Okay, so if you pull it the same speed,
Yeah.
you pull it against the notches only. So in other words, you are pulling 6, for example, that's 9 notches, okay? And in 1 second you pull it 1 time, so 9 notches each second. So isn't this the same data? Why is it different? Why do you do this interval notches? Why is the significance of this data?
Because we want to know if we change the interval, we will change the research of the experience.
What about for different number of notches, but then same interval? And different interval, but then different number of notches. Okay, what do you think will happen? Any idea? I'm curious.
Might be more fast.
For more or less?
Maybe more maybe less.
Do you think there will be a threshold, for example, for this number of notches and any increase will not increase anymore? Do you think there will be something like that? Yeah. Okay. Can you show me other graphs? Any other graph? Because I don't know what I'm saying. Can you show me any else? Yeah, the one more.
What is the kind of
So now each team have 2 minutes to prepare your conclusions. the preparation time is up. Now I would like to ask Deep Explosion to make your summary or conclusion.
Okay, first we'll start with our own presentation. We have a lot of data and a lot of factors for the data, but then we find our own experiment data to be have high errors, as you can see for the plot. But then, it's only for specific system, for specific length of rod, specific length of string, type of string, only one time. And we have a lot of high errors, But then we use it to fit our formula. And we find it to be a good fitting, so we indirectly can prove that our theory is right. And for the opponent's presentation, there's a few factors only, and they change the system, and they have high consistency and accuracy for the data, which is good. But then they do not compare their results with their formula, their theoretical formula. For example, they don't calculate the kinetic energy and the relationship between the velocity, pulling speed, and the angular momentum, the angular velocity. I think that is a shame and it can be done better. That's all. Very well done. Thank you.
Thank you, team. So now it's team A's for your conclusion.
I think my formula from our theory is full and clearly, and we show our parameter affect the regional, intra, and angular velocity by our formula simple variable. And our experiment design, we decrease artificial errors by voice frequency software and show regular parameters to notch interval and regular length change, and choose the exact material of steel. Then we get a good result from theory. KR in proportional to rotational inertia, and KR equal to omega squared. And to another side. I think your proposal is very detailed, and your design your effect parameter is simple. Yeah, good. And your proceeding of your will be simple, but you can change you can decrease your artificial error, and you can choose another material of your stick. That's all.
So thank you for both points conclusion. Now it's time for the jurors to ask questions. So any questions from you? So both being presented, please.
I have a question for both teams. First, to Team A, in your G-Haw experiments, I think in one of your slides, you said there's no potential energy involved, right?
Yeah.
Okay, if there's no potential energy involved,
Yeah.
then how does your pulling kinetic energy transform into rotation? What is the mechanism? How does it transform?
The energy transfer to the nails and negative oscillator.
Yeah. Meaning the kinetic energy transform into what?
The energy transfer to the nails. Nails.
Which nail? The nail on the tip? The nail that connects the propeller?
The nails and these bolts.
Yeah, but how? I mean the process. You're pulling kinetic energy through what channel turns into the effect into
Because
your
when
wing?
it fits the stick in the same height, so the potential energy equals to
But you said potential energy is zero. There's no potential energy involved, right? But in fact, there is. There is potential energy, elastic potential energy. So each time you hit the notch, your stick actually deforms. So it vibrates, right? So that's the channel. The pulling kinetic energy transforming in rotation. The second, okay, well, I'll give you the second question after my question to Team B. I think in your page 17. Please show me page 17. No, I think there's a slide you compare the free fall with the chain table. Yeah. This one. Oh, okay. So what is your vertical axis?
I'm sorry, it's more. Time taken T. So time taken for it to fall from the same height.
Okay, so it seems to me that your results tells us that the more staking, the more blocks you use, the behavior is closer to the free fall.
Yes.
Is that right?
There's less increasing velocity.
Less increase. Okay.
Yeah, less
But it
velocity is
seems
lower.
to me, each time when one block hits the table, it inserts an impulse from the other end to the rest of the system, right?
Yes.
Therefore, the larger number of the blocks, the more number of impulse inserts.
Yes.
So the result should be much more different from free fall.
Okay.
How do you account for that?
So we say it is more than free fall because we say this velocity here, the tensor motion, is the velocity 2v about 2d cos theta. But then we did not look at sin theta. So for high angle, sin theta is significant. And sin theta will pull the string up and it causes low chain, which is as the video following. You see, in some cases, they actually pull the string upward, which causes there's no increase or either there will be a decrease in velocity. And this angle, we did not set the angle as high as this. Normally set it about 30, 35. But then as it collides, the more it collides, the more collision it has, the more chances you will get the angle higher than 44.4. Because when it collides, the second block up there will have a high angle due to collision, due to pulling of the string. So when this second block collides with the surface at high angle, you have more chance to show case of slow chain, which will decrease the velocity of chain. So the more block there is, the more chances of slow chain happening, and then you have more chances of having the same velocity as free fall. There is actually an increase in velocity before, but then later you decrease it back due to slow chain. And the slow chain happens because of sin theta, which is, if you look at our formula, right here. We look at the circular motion only. We look at the tangential velocity, but not at the radial one. And if the theta is high, tangential velocity is upward like that. And it easily collides in the second block or pull the second block upward through the string. And this will cause a decrease in velocity.
So you're saying that the stick that hits on the table actually pull the second
Yes.
block through the string?
Because first, there will be two velocity, one is tangential and one is radial velocity. If the theta is high enough, the theta will be like that, for example. The radial velocity will push the string upward due to collision. So like elastic collision here, slide upward.
But your string is soft. It's not a rigid body. Even
No.
the tip swings up.
There is a different study. It does not immediately pull it up, but then after it flies up high enough, as you can see for this one, it pulls high enough, and then the second block changes its angle. You see, it did not collide with anything, but then it changes angle due to the string pulling. There's the side with shorter string, and this side will pull the string upward, which changes the angle of the second one, which causes it to have a slightly low angle.
Even so, does it have any effect to the rest of the system?
If you look at the second case, it did not only cause its angle to be 0, it actually pulls. The fourth one. Actually pulls the block up. This is in higher height. It not only changes angle, it actually pulls the block upward. And this changes the initial velocity of collision for the second block. And if the initial velocity is lower, it will cause the whole system to experience a lower thing. And thing is, actually, when the first block collide, the third block is not affected. Only the second block.
Did you make a video to compare free fall and
Yes.
in the photo? Did you see the force? I mean, in pace, in phase?
If you look at the graph, there is a slight difference in time for number of blocks higher. There is a difference in time, but then it will be lower for more number of blocks. And if you look at this, this has 11 blocks in it, if I remember correctly. And for 11 blocks, the time difference is really, really small. And this is in 1,200 frames per second. So this whole system will fall to the ground about 1 second or more. And there is only a slight increase in time. And this slight increase is what we observe and what we say.
All right, the final question. Do you consider air resistance? Because the stick you use are pretty light.
Yes, air resistance we did not consider it because two reasons. One is complicated. It's really complicated. When you consider air resistance in circular motion and all those motion, it's really, really complicated. And secondly, because free fall system and the fast chain experience the same air resistance when falling down, but not circular motion. And the time of circular motion is 0.05 seconds. So we actually take it as negligible. Is it like that? We do not know. It's really complicated. We do not have the time to do it, and we do not want to do it. So yes, we will accept it slightly.
The second question, I'm sorry, maybe a 3 joules provides more time for us. The second question for the G-How. Did you examine the way you pull the second stick? It's on the top, on the right, on the left. Did you do that?
Also, when we test the video, we grab the notch D on the same side.
So you always pull on the top.
Yeah.
Thank you. Any other questions?
How do you obtain this 44.4 degree
From a lot of data.
from experiment?
Yes.
Okay.
For experiment.
Okay.
About
Okay.
this angle, there will be.
Okay, that's all I get.
Thank you.
Any other questions? So then, I think there's not enough time to answer my questions. So I think we will stop here and let the thank both teams and let the jurors to have their scores. Sit down. Okay. So let's show the scores for Team A. So the scores are 7, 6, and 7. I'll show the scores for the Team B. Okay, please. So the scores are 7, 5, and 8. Now, any from the jurors would like to give some comment or encouragement to the teams. It is also possible to speak in Chinese.
OK，境内因为你这两个实验我都做过嘛，事实上你应该要去examine在不同的这个部位的位置，你会发现你的 stick 的旋转的方向是不一样的。那你旋转方式不一样，顺时针、逆时针会带动你的 propeller， 就很像你在摇打圈一样。OK， 所以你的手指也许就扮演一点点角色，但事实上会影响到它正转逆转，是你这个刮的这个方向 方向才是最重要。不过你们有一个很不错的做法，就是你们用这个声音的这个波动来看你这个功率的这个态势啊。那事实上就是当你一个棍子在某一方向有切割的时候，这个棍子在这个方向的这个 modulus， 这个 shear modulus 跟这个又是不一样的。所以你每次刮的时候，这个你刮到这个凸起来之后，你会把它压下去；你刮到呢凹下去，稍微弹回来，对吧？好，但是因为这两个方向的 modulus 不一样，所以它不是这样的，而是这样，会造成旋转，所以才会带动这个道理。这是我提供给你们的经验。那第二个，我实在是认为你的实验做错，因为你掉下来的过程中，你每一次敲到桌面的时候，你都给剩下来的系统一个 impulse。你棍子越多，你给的 impulse 越多，所以这累积出来的这个结果，一定会使你落在桌面上会比 freefall 快。你的东西越多，会快的差别会越大。那这是你们实验的结果，这个跟这个分析是完全相反。我认为你们这个误差的所在是在于你们的 stake 太轻，所以事实上空气阻力占用是重大的。你们才会有这个。虽然你们做了很多分析，而且其次，你们用的线在这种量的 impulse 里面，它事实上即使它有形变有延长，那是可以忽略的。对吧？这是我的看法。
不好意思，我比较不会说他们做错，至少他们呈现的是跟他们结果一致的东西。我会说的就是，如果我同意林老师说的，用的材料是比较不见得那么恰当，就是我没有用他们做错的这个词。
好，那这样好，
我的看法跟林老师一样的。
好，这也许我应该说回来是没有什么做错做对，就是你们呈现你们的这个结果。但是我这样讲，就是说你们实验里面的误差，事实上涵盖你们要观察的。我应该这样说。
我觉得比较高分是因为不是因为说你们做的那个结果是很好的、很对，而是说你的呈现是很好的。不管你最后那个结果是不是真的很完整，或者你的呈现跟你的做的东西那个呈现的过程比较，理论与实验的比较，这件事情做的我觉得比较高的。
那我最后说几句话，就说针对这个官校这个，就说我是觉得说你们在分析上面有取得不少数据，是有些部分事实上还可以再仔细看一下。比如说像我们第二部分就是说不同的interval，但是你其实量到，其实你看一下那个图形，有一些地方有不一样的趋势，有的那像那些指导是可以再多讨论一下。那像这个那个Exlosion对，我成功大学，我是觉得说，对我同意，其实同意两位老师说，就是说你们实验这样做和分析，但是我是觉得你们可能主要是分析的方向错了，就是说因为你们分析第二根棍子，可是问题就是说那上面的棍子发生什么事情？那事实上应该我说不是说错，就是说其实还可以多分析一些东西，不是只分析第二根棍子，如果不管是3跟4根，上面的棍子可能都要去注意一下发生什么事情。那另外最后是提醒一下，其实这个给两位同学经验，像这个 Exlosion 对这张图，他们下面做一些 fitting， 可是做 fitting 的时候很重要一件事情，就是你那个参数它对应的这个物理是什么？就你们做了很多 fitting， 然后说这样子 fit 这样子，就说这样子可以 fit 出来，这样可以 fit 出来，这样可以 fit 出来，可是那它的物理对应的是什么？就事实上并没有告诉你，那很可惜。那还有最后一点就是说，市场发现我们这个比赛，事实上也是个团队合作比赛。不过整场看下来，就是说，事实上好像就是这个题目好像就是全队就是2、3位同学，感觉好像2、3位同学参与，并没有那种好像很整体性的感觉。那这个事实上大家可以试着想想看，还有什么样可以互相协助来做一些更好的突破。好。 那么还是一样，就是谢谢两位同学的表现。那么谢谢大家。